Hello guys, today in this video we are going to discuss about non-uniformly doped PN junction, right? So till now we have discussed uniformly doped PN junction, and for uniformly doped PN junction we said that the N region will be doped with donor impurity concentration, and we consider, suppose this is your bulk material, right? So this is N region and this is P region. The N region is doped with some impurity concentration ND, donor impurity, and P region is doped with acceptor impurity Na, right? Then we said there will be a depletion region created over here, and this is known as the space charge width. These abrupt boundaries we consider to be xn and minus xp. This is the metallurgical junction here, x is equal to 0, right? And uniformly doped. So if you will do the charge distribution for this, then we said this is plus xn and this is minus xn, to which up to which the space charge region is extended, right? And the charge distribution, you got this is x, the length, and this is the charge volume charge density. And this charge density here we said END, because positive space charge region created here, right? Positive space charge region in the N side and negative space charge region in the P side. Okay, so positive and negative space charge region, this value we said minus ENA. So one thing you need to notice, that the volume charge density in the space charge region or the depletion region remains constant. You can see that the value END and minus ENA, these are constant, right, independent of this. If you see, okay, they are not actually changing in the depletion region with respect to length. But here in a non-uniformly doped PN junction, we will consider a different kind of charge distribution, where we said it is a graded impurity. Graded impurity means what? Continuously increasing, concentration like this. And suppose I will show the charge distribution this way. This is the dimension of the space charge region here, and let us take it as plus x0. Similarly here it is minus x0 here, okay? And you can see it's not constant, it is varying. You can see it is in increasing slope with a constant slope. To keep it mathematically simpler, we consider non-uniformly doped PN junction. But you can see here, if you will take the rho, the volume charge density, and x, okay, so if you will take rho by x, it is constant, right, with a constant slope, you can see, right? So the space charge region here, positive and negative space charge region, and you got rho by x is equal to constant. So what is that constant here in this region, N side and P side? If you take rho by x, let us consider here to be plus E as the charge, and A is the rate at which it is increasing, right? So rho by x, you can say E because of the positive charge, and A at which it is increasing, right? So we consider non-uniformly doped PN junction, but it is actually a linearly increasing function, linearly graded impurity distribution, you can say, right? The same thing for this region, P region, you can write rho by x is equal to minus EA. So either you take N region or P region to determine the value of electric field or potential. It will give you the same thing, same result. You can see a symmetric linear line, okay, crossing through x is equal to 0. So the variation is symmetric in both N and P region. So it's, you can take either the P region or the N region. So I am taking the N region, right, to determine the value of electric field over here. Okay, you can see, compare these two charge distribution, then you will be able to find out the difference between uniformly doped PN junction, the depletion region, the abrupt boundaries here, and a linearly graded impurity distribution, where we said there is a constant slope, and you can see rho by x is having a constant slope, constant gradient, and that gradient is EA here in the N region, minus EA because negative charge you can see here, so minus EA for the P region, right? So using the value of rho, we will be able to, rho is equal to EAX, as you can see rho is a function of x, and considering this rho value, we will be able to find out the electric field. So let us do that. So we will start with this rho value. There is the volume charge density, the charge distribution in the depletion region, that is important for us to determine the value of electric field. So you know the relationship between rho, that is volume charge density, and the electric field, how they are related. So in 3 dimension in electromagnetism, if you have done del dot E is equal to rho by epsilon, and epsilon s I am writing for the semiconductor. So electric permittivity of the semiconductor, right? So this we can write actually in 3 dimension. But in 1 dimension, if you want to write, simply it will be d by dx is equal to rho. We said it's a 1 dimensional function of x and epsilon s, right? Now if I want to find out electric field over here, rho x epsilon s and then dx, then you integrate it, right? Substitute the value, take the constants out, 1 by epsilon s constant, then you got ea x, so ea out, and then I substituted rho x is equal to eax, rho is equal to eax, substituted over here, ea constant took out, epsilon s took out, so we have x dx over here, right? So ea by epsilon s and x dx we can write as x square by 2 plus some constant of integration I will write, okay, because it is indefinite integration, there are no limits here, we have not given any limits, so constant of integration we need to take into consideration, right? After this we need to evaluate the value of this constant of integration. So by using proper boundary condition we will be able to evaluate the value of C1. So what boundary condition we will take, right? So for n region you can see at x is equal to x0, this up to this actually your depletion region is extended, you can see towards the n region, right? At this x equals to x0 is the neutral region, from there the neutral region starts, okay, there will be no space charge here after x equals to x0 or exactly at x equals to x0. So that we can consider as the boundary condition to evaluate the value of C1. So what I will say, at x equals to x0 here in the n region, right, electric field is 0, right? So if I will substitute that, so what we said, electric field is equal to 0 at x is equal to plus x0, that is in the n region, right? Let us use this as a boundary condition. Substitute, electric field will be 0 when Ea by 2 epsilon s, okay, and then x I will substitute as x0, so x0 square, Ea by 2 epsilon s x0 square, then plus C1, right? So you can rewrite C1 is equal to minus Ea x0 square divided by 2 epsilon s. Okay, now you substitute here the C1 value that we got here. C1 is equal to this, substitute it here and rewrite what is the value of electric field in the depletion region. So what will be the value of electric field in the depletion region? We can rewrite it as electric field E is equal to Ea x square divided by 2 epsilon s, okay, and then C1 value which is minus Ea x naught square divided by 2 epsilon s, right? Take everything whatever can be taken common, 2 epsilon s we can take, and here we got x square minus x naught square, right? So this is the expression that we got for the electric field in the depletion region. Now we can use this expression for electric field in the depletion region to obtain the potential in the depletion region. So how to obtain the potential in the depletion region, right? So once you got the electric field value, you know the relationship between the electric field and the potential in 3 dimension and what we will write in 1 dimension, right? So in 3 dimension we know the potential and the electric field are electric field and the potential are related like this, del phi, E is equal to minus del phi, negative gradient of the potential will give you the electric field. Now in 1 dimension we can simply write, okay, E is equal to minus d phi by dx, d phi by dx. So we can rewrite it. If you want to find out phi, then you take E dx with a negative sign and integrate it, right? Okay, we have the E value as a function of x, we can substitute here, right? So let us substitute it. So you have the minus sign, whatever constant term I will take it out, Ea divided by 2 epsilon s, okay, inside the integration we have this function x square minus x0 square, right, and then dx. This is what I got for the potential. Okay, let us now integrate it. If I will integrate it, what we got? Minus EA by 2 epsilon s will be there, right? And then you got x square dx will give us x cube by 3, right? Minus you got x0 square dx. When you will integrate, it will give us x0 square dx, integration will be x, right? So this is the value we got, and some constant of integration, again the same thing, it is an indefinite integration, right? So we need to, second step is we need to evaluate the value of C2, okay, by using proper boundary condition. Okay, I erased it, I am going to use it again, I will tell you. Okay, so what boundary condition we will use so that I can obtain this C2. So let me redraw the charge distribution. This is x and this was your rho value, and then here you got your minus x0 and this was your plus x0, right? Minus x0 and plus x0. Now here we said in the while determining the electric field for the electric field, when we determine we put the boundary condition to determine the constant of integration, we said at x equals to x0 electric field will be 0, E is equal to 0, and here also at x is equal to minus x0 E is equal to 0, because at this point at x equals to minus x0 and at x equals to plus x0 the neutral region starts, right? But in case of potential, you cannot substitute that phi at x equals to plus x0 will be 0. No, it will not be 0. What will happen here? Because here you got the positive space charge region, negative space charge region here. So negative space charge region means what? This is the minimum potential. Here we got minimum potential, right? And this will be the maximum potential, and we don't have any finite value for maximum potential, so I cannot write at x equals to x0 this phi x will be this value. So what we can do is, for minimum potential we are aware of what? Now phi at x is equal to minus x0, this is minimum means what? 0. Okay, it will start from 0 potential and then will reach to maximum potential, and that maximum potential is nothing but the built-in potential barrier. Okay, same like we have done in thermal equilibrium case for a uniformly doped p-n junction, so that gives you the band bending, right? So here also the same thing you can see. So minimum to maximum potential, so that minimum potential we can consider 0, so it will start from 0 to reach to a maximum value of this VVI. Okay, so let us consider this boundary condition. So what I will take, phi at x equals to minus x0 is 0 in this expression to determine the value of this constant of integration. Okay, let me erase this, and then we will substitute the boundary condition as I said. So phi is equal to 0. Okay, phi is equal to 0. Phi is equal to 0 at x is equal to minus x0. Okay. Okay, be careful while substituting these values. There is negative sign, so you can see here what we got. Phi is equal to this. Phi is equal to this. So 0 is equal to minus EA divided by 2 epsilon s, and here in the bracket we have x equals to minus x0, so I got minus x0 cube divided by 3, and minus here we got x0 square and minus x0 minus plus x0 cube plus x0 cube we got, okay, and then plus C2. This is what we got, right? So now we can rewrite 0 is equal to minus EA by 2 epsilon s. Solve this bracket, you got 3x0 cube minus x0 cube, that gives you 2x0 cube plus 2x0 cube divided by 3, right? So this is what we got, plus C2. Okay, so now C2 can be written as, if you will take this side, it will be positive, so EA divided by 2 epsilon s. Okay, and sorry, 2 got cancelled, so you got 3 epsilon s EA divided by 3 epsilon s x0 cube. Okay, EA x0 cube divided by 3 epsilon s, that would be C2 and the positive sign, right? Yeah, so we got the value of C2. Let us now substitute here in the original phi value. So now we can write the phi value by substituting C2. By substituting C2 that we got. So phi now can be written as minus EA by 2 epsilon S. Okay. And here you got x cube by 3 minus x0 square x plus C2 here plus EA x0 cube divided by 3 epsilon S. This is the value of potential in the depletion region, okay, when there is no applied bias, okay, in a graded impurity or non-uniformly doped PN junction, right? Okay, so now what I said just now in the boundary condition, I told you that phi value at x is equal to x0 plus x0 is nothing but the built-in potential barrier, if you remember. So we got this distribution. We got the minimum potential here 0 and the maximum potential here, okay, which is VBI, right? So at x is equal to x0 plus x0, we said this is maximum and the value is built-in potential barrier VBI. So we can substitute like x equals to x0 and then we can write this potential is nothing but the built-in potential barrier, so that we can write built-in potential barrier in terms of x0, okay. So let us write that. Well, so what I will do is I will substitute x is equal to x0 and I will write phi to be VBI. So I can write phi is equal to VBI, that is built-in potential barrier, and carefully substitute the value EA by 2 epsilon S, and here we got x0 cube by 3 minus x0 square and x0, that makes x0 cube plus EA x0 cube divided by 3 epsilon S. Okay, so this is the value. Let us now substitute like whatever we can take common and all. So here you got minus 3x0 cube plus x0 cube, that gives you minus 2x0 cube by 3 x0 cube minus 3x0 cube makes minus 2x0 cube by 3, okay, and then here you got minus EA by 2 epsilon S, okay. So 2 got cancelled, right, that, and here you have this plus EA x0 cube divided by 3 epsilon S, okay, 3 times epsilon S, right. So minus minus plus, you got EA x0 cube divided by 3 epsilon S plus EA x0 cube divided by 3 epsilon S, so that makes 2 times EA x0 cube divided by 3 epsilon S, that is our VBI. So built-in potential barrier we got the VBI value to be this, okay. So VBI we got in terms of x0. So VBI, the built-in potential barrier in a graded impurity distribution PN junction, okay, or a non-uniformly doped PN junction, we got the VBI value in terms of what? The abrupt boundaries of space charge x0 for a at a constant rate doped semiconductor. A gives you what? The density gradient, right? That is the volume charge density per unit length. That's the value EA, you can see, right? So we got VBI is equal to twice of EA x0 cube divided by 3 epsilon S. So if you know the value of VBI, then you write x0, make x0 cube the subject, and then you find out x0 cube is equal to 3 times epsilon S VBI divided by 2EA, right? Okay, and if you want to write what is x0, then you take 1 by 3. Okay, so you got the value of x0, that is the abrupt boundary, okay, of the space charge region x0. Now what is the region that we wrote x0 in terms of VBI, because VBI is a known value from the doping concentration and all, we can find out this VBI. Now knowing this dx0 by dVr, we will be able to find out the junction capacitance. Okay, anyways, we will continue that in the next video. So for here our objective was to determine the potential and the electric field and the built-in potential barrier in terms of x0, or you can say x0 in terms of the built-in potential barrier. Okay, thank you for watching. We will continue deriving the junction capacitance for a non-uniformly doped PN junction in the next video. Thank you.